Electric power is a pretty big deal for us. Most of us automatically associate electric power with the electricity we use to power the dozens of devices we have in our homes. We can describe it in terms of the wattage of our light bulbs. We can talk about the power transmission lines. These are all examples of electric power and energy and how we use it. Remember that power is the work done over time, and this relates back to the change in potential energy over time. Also remember that we define electric potential energy as the change in electric charge times the voltage, so we can substitute that in as well. We also just recently learned that the change in charge over the change in time is the current flowing through a circuit. So now we can write electric power as the current times the voltage. This equation holds true for any electric circuit that you apply it to. Now we know already that power is labeled as watts, so 1 watt of electric power is 1 amp times 1 volt. We can come back and apply different versions of Ohm's law to create different descriptions of power going through resistors. First, we can take the V equals IR and plug it into the V for the power equation. This gives us power equal to current squared times resistance. You will oftentimes see this referred to as the Joule heating equation because it is really describing how much heat is being created as you add more and more current into your circuit. The other option is to solve for current in Ohm's law and substitute that into our power equation. We end up with power equal to the voltage squared divided by the resistance. This implies that the lower the resistance connected to a given voltage will result in more power. Also, if we increase the voltage, the power increases exponentially. Now keep in mind that these equations are only valid for a circuit that obeys Ohm's law. The P equals IV is usable for any circuit, but the other two only work for ohmic materials. The equation that you choose depends on what is being held constant in each situation. For example, if you're holding the voltage constant and want to know what happens to power when you change the current, you would use P equals IV. If you were holding voltage constant and changing resistance, you would use P equals V squared over R. So you need to know what the system is holding constant in order to determine which equation to use. Say we increase the resistance in a circuit and we want to know how the power changes. Well, it depends. If you are holding current constant, then the power will increase according to our second equation. If you're holding the voltage constant, then the power will decrease according to our third equation. Electric appliance usage is billed in kilowatt hours. This is just a convenient way to say how many watts of energy you use for a given amount of time. It is actually a measure of the amount of energy that is used. We can see that if power is equal to the energy over time, then the energy is equal to the power times time. Power is measured in watts, or thousands of watts, times the time, which comes out to kilowatt hours. We can determine the exact amount of energy by taking 1,000 watts and multiplying it by 3,600 seconds. So 1 kilowatt hour is equal to 3.6 times 10 to the 6th joules of energy.